Hi, I'm Chong Zhu, a first-year PhD student in Center for Quantum Information, Tsinghua University. Today, I'm here to give a brief introduction to our recent paper, Experimental Demonstration of Quantum Gain in a Zero-Sum Game. In this paper, we propose a zero-sum game described as follows. The referee sends out the input state, which is a 2-qubit state, row AB, to player A and B. This row AB is required to be symmetric to A and B under the exchange of subscripts. And for a classical game, player A and B can do arbitrary classical operation to their bit, and then measure it in computational basis. We assume that A wins if the measurement outcomes are identical. Otherwise, player B wins. We further assume that the diagonal term of row AB are R1/4, which corresponds to a classical Nash equilibrium, with each player have 50% winning chance. And now we assume that player A has some secret quantum power, which means that he can do arbitrary 1-qubit operation to his bit before the measurement. Now we're wondering, how much can player A gain from this balanced Nash equilibrium? We also use entangled photon source to experimentally demonstrate this quantum gain. We find out that the quantum gain depends on the form of row AB. And if row AB is a maximally entangled state, player A, in principle, can win the game with 100% probability. And in our experiment result, it shows that the player A can win with a winning chance of 94.3% probability, which clearly demonstrates the significant gain of the quantum player. Now, we're wondering, what property of row AB characterizes the gain of the quantum player? We find out that quantum discord, another type of quantum correlation different from entanglement, also determines the quantum gain of player A. Surprisingly, we find out that entanglement is not necessary for quantum player to have a positive gain. There exists state with no entanglement, but non-zero discord, leading to a positive gain. And our experimental data agrees with our theoretical predictions. We can see from this figure that the quantum gain remains positive when the entanglement disappears at p larger than 0.3, and the quantum gain approaches to 0 along with the quantum discord, not the quantum entanglement. Okay, I think this is all our results from our recent paper, which will be published in New Journal of Physics. Thank you very much.